Okay, I'm going to present the work of Sven Rödlöbers, a colleague of mine and a project partner of Mediri. And clinical application of for focus ultrasound in abdominal organs is not very widespread in the Western world at the moment. Mainly due to two challenges that we faced. One is the occlusion effects by the rib cage, and one is organ motion. And if you want to compensate from organ motion, you somehow have to track the motion and assess it. And there are a couple of requirements for a tracking algorithm that tracks organ motion. First, it has to be precise to actually compensate the motion well. Second one, it is typically employed in real-time scenarios, so that it also has to be very fast. It has to be safe in the sense that if there are tracking failures, we should be aware of those and treat those. And lastly, it has to be automated, or should be automated, so that you don't add more cumbersome work to the already very complex setups that we face in these scenarios. We present a tracking method in this submission here that is able to track motion on ultrasound and MR images. The choice of tracking modality is something that that is open here. So for example, if you want to be independent of MR imaging to increase the scan time for other monitoring tasks, you can use ultrasound tracking. Or if you say, okay, I want to reduce my hardware setup, I'd rather use the MR imaging as my tracking modality. This method works on both. Besides being agnostic of this modality, the tracking method is also automated, so the feature selection is done automatically, and we have a quite robust method by employing a multi-scaled scheme where we first globally find an alignment of the tracking features and then go into the individual scale. Furthermore, we have a quantified uncertainty for our tracking method, so this is comes in really handy, and I'm going to explain that later on. The method is based on a particle filter approach. But first thing is that we do an automatic feature selection here. So we find distinctive points or landmarks within the liver automatically and reduce them to a subset of feature points around this tracking, around this landmark. So we have here feature points that are in a pattern that describes points in the image with higher and lower intensity as compared to the tracking position. And those feature points are then taken as our tracking features. Those tracking features are then allowed to transform within linear transformations, that is scaling, rotation, and translation, or a subset of that, if you wish. And this is done, as I already said, in a two-level approach. So first, a global net transformation is estimated for all tracking features, and then local deformations of the tissue are accounted for by local optimizations of the tracking feature points. The particle feature approach means that we don't employ traditional optimization techniques, but our feature point trajectories are optimized by generating a set of hypotheses, and a hypothesis is more or less a point in the linear transformation feature space, and this set of hypotheses forms a point cloud in this linear transformation feature space. By weighting each of those points in the cloud with their accordance to the actual observation, we can then do an averaging of those of this point cloud, and the center of this point cloud delineates the tracking feature position, and the spread of the point clouds gives us an estimate on the uncertainty of the tracking. This comes particularly handy if we want to actually detect tracking failures, that is, for example, unforeseen changes in the tracking, in the motion pattern, or imaging error, or even poor modeling of our tracking method. For example, we employed, to visualize this, we employed a good model that actually has prescribed parameters that have plausible motion magnitudes, and an implausible parameter set that estimates those the motion magnitude too low for liver motion in this case. So on the first side here we have the initial feature set, and then we let the algorithm run for some seconds. And then we look at the result of the tracking, and you can see that the uncertainty is visualized by the size of the circles here, and our poor model choice actually has bigger circle size, indicating the higher uncertainty of the tracking feature. All right, we evaluated the method in two challenges, one MR tracking challenge and one ultrasound tracking challenge. Both were compared to manually annotated landmark positions. For the MR tracking, we reached an accuracy of about 1.7 millimeters for 2D sagittal APIs of the liver. Can you play that movie, maybe? Okay, and here you see the tracking points following the trajectory. And the second challenge was an ultrasound tracking challenge, if you can play that movie as well, please, where we had 2D ultrasound images and 3D ultrasound images to evaluate the tracking method on. And we reached a mean tracking error of 1.5 millimeters for the 2D ultrasound case and 2.8 millimeters for the 3D ultrasound image case. In both cases, the processing time was about 2 milliseconds per frame, which is within real-time capabilities. So the method is applicable for real-time. So to conclude, the method is able to track features on MR images or streams of MR and ultrasound images. It is reliable and precise enough to be used in HIFU therapy devices, and it is able to do that in real time. Consequently, we integrated this tracking method within our Transfusimo treatment system, and as you heard earlier, we are going to we have a clinical study scheduled for 2017, and we are eagerly waiting for results from that study. Thank you.
Are there any questions?
I have one question. This is mainly designed for respiratory motion.
Right.
Do you have any considerations of unexpected movement of the patient?
Yeah, so this is actually it is not necessarily a periodic motion that we can track with this, so it can actually track any kind of motion. However, the motion magnitude somehow has to be estimated. The expected motion has to be estimated before to parameterize the model, which I showed you with the uncertainty of the model there. If we have if we encounter coughing or other unforeseen motion, the uncertainty of the tracking features will blow up, and you at least know it, and you can say, okay, from my uncertainty threshold is surpassed, and I have to stop sonication right now because I can't say can't actually provide valuable information about the tumor position or target position at the moment.
Okay.
Right.
Thank you very much.
Thank you.